Right. Good morning, all. Okay. So last week, so we stopped at the work and kinetic energy. All right. And then we don't have lecture on last Thursday because I wasn't feeling well. But we will continue from that. So some information regarding your test one. So your test one is will be until only chapter 5. All right. So this is already chapter 6. And today we're going to also look on the chapter 7 as well. Okay. And any other question before we start? So basically there will be 4 questions. So the question will consist of the chapter 1 and 5. Okay. All right. So if there is no question, then let's start with the chapter. Okay, let's continue with the chapter 6. So last week, so we discussed about the work and kinetic energy. All right, so we already discussed about this. So we know that the work done by the external forces acting on the scatter, all right, in this picture is 0 because the scatter's kinetic energy change, all right. Okay, but the thing is, the normal force acting on the body is similar to the force that is right to the weight force. Okay, so that's why uh, the external force acting on the scatter is 0. All right, so let's see about the relationship between work and energy. So the many forces are not constant. Suppose a particle moves along the x-axis from x1 to x2. Okay, so you look there, then you see that the graph is not linear. Why it's not linear? Because let's say there is, if you pull the box, then the force is not constant. Then of course it will vary. All right, so the force will vary according to the time. Right, so at certain point the force will be much more than the force at a point later. All right, as you can see on the graph. So between x1 and in the middle of x2, in the middle of between x1 and x2, the force is not much change because the force is not as bigger, is not as big as the force in the middle of x1 and x2 to x2. Okay, so over there the forces are not constant. All right, so how to find out the work done by the force if it is not constant? So we need to find out the area under the graph, but you need to take some segments. All right, so you take multiple segments. From there, let's say you can see the graph on the right side. So let's say you make multiple segments such as there. Okay, so you calculate the forces at each segment and then add all the results for all of the segments. Okay, so basically it is integral form. So where the weight is x2 to x1, so fx is actually the summation of the area, all right, area under the curve, all right, of segments. Okay, so this is how we do the calculation. All right, so let's say we have a constant force. Okay, so what's the work there? So the work is the still area under the graph. Okay, so W equals to Fs. So we need to find out what is the force. Okay, and S is the displacement, meaning that x2 minus x1. So it's actually area of the rectangle area. Okay, in terms of a spring, okay, the force required to stretch a spring distance x is proportional to x is equals to kx. Okay, so you know that the force required to stretch a spring is Fx, and then so this is linearly, all right, linearity is linear to the displacement, all right. So as you can see there, so we have work as half kx squared, all right. So why? Because the length, all right. So the area and the triangle area, so we have the length and the width are similar. So both of that are x and x. Okay, so you have k. So k is actually the slope, right? The slope of the graph. So you obtain that W is equals to half kx squared. Okay, if you stretch the string, you see that when you pull here, okay, when you pull here, then you have a force Fx, okay, at a certain distance. For example, like this one. So you have another force pull on. So minus Fx, and then this is plus Fx. Okay. So over there, the force is in the equilibrium. Okay, for motion, all right, so let's say the particle move from point P1 to point P2. So you have the force that varies uh, in the magnitude and also direction. Okay, so the work can be found using a line integral. Okay, so work is equivalent to this equation. All right, so you need to find out what is the okay, so what you need to integrate, okay, from P1, from P2 to P1, the line integral of that, and then based on the force given, right? So you will obtain that the F dot dl, so you have an angle phi. So this is because you need to find out the when you multiply with the cos, all right, so cos will be this force, all right. So this is the line integral over here, so that's why you obtain cos theta of fx of s. Okay, so basically you find out what is this equation, what is the solution for this, and then you integrate P2 to P1. Okay, right, so that's how you perform the calculation. All right, so let's finish up with the power. Okay, so for the video here, you can have a look. Okay, so this is another example on work energy theorem for the motion along a curve. All right. So I'll go straight to the power. So power is the rate at which work is done, right? So average power, all right? So it's just you find out what is your work, okay, for a certain, let's say for a certain period, okay, and then divide with the time taken for the work to be done, all right? So you obtain the average power. For example, you have a different W, let's say W1 and W2, and then T1 and T2. So your average power will be W1 and W2 minus W1 over T2 minus T1. Alright, for instantaneous power, so you look at the specific work during that time, divide by the time, okay, the time at that specific uh, work being done. Alright, so you have the instantaneous power. Okay, the SI unit of power is watt, right? Or joule per second. Alright, so because work is joule, divide with time, second, so joule per second. Okay, let's say we have a problem here. Let's say you want to lift a box slowly. Okay, so work you do on the box to lift it in delta T equals to 5 seconds. So you lift up. So you lift up an object. Okay, so you lift up an object. So up to 5 seconds. Alright. And the total work done. So the change of work, okay, from here to 5 seconds is 100 joule. So average will be 100. Average power will be 100 divided with 5. So you obtain 20 watt. Okay, so if you lift a box quickly, will your power will be higher? Of course, right? Because you need to give a bigger force to make the box move quickly. All right. So here the work, all right. So the work is still 100 joule. All right. Similar work is 100 joule, but the time is only 1 second. So the power will be much higher compared to previous one. You only use only 20 watt of power. So whenever the time taken is lesser, all right, the power will be higher. Okay, remember that power depends on time. Okay, so we also define the power in terms of force and velocity. All right, for example, we have the instantaneous power. Okay, force is equals to force dot v. All right, v is the velocity of the particle. All right, so that's it for the chapter 6. All right, we will continue with chapter 7. So far you have learned on how to, all right, you have learned about the concept of force, concept of work, all right, and concept of power, all right. So in the chapter 7, we will discuss about the energy. And then you remember that in the chapter 1 is only about the basics of SI unit and the vectors, right? And then chapter 2 to chapter 5, you will discuss about the Newton's law. All right, you discuss about Newton's law and how to solve that. So meaning that you have multiple, let's say you have multiple forces available, and then you need to define. We have three Newton's law. First Newton's law, second Newton's law, and also third Newton's law. So you need to able to distinguish which Newton's law is applicable for each specific problem. Okay. All right. So we are in the chapter 7. We are discussing the potential energy and energy conservation. All right. So this is what actually we will learn about the gravitational potential energy. So you learn because you already learn about the gravitational acceleration, gravitational force. All right. So now you also learn about the gravitational potential energy. Okay, and how to use the elastic potential energy as well. All right, the distinction between conservative and non-conservative forces. Okay, and then how to use energy diagrams to understand how an object moves under the influence of conservative force. Okay, so how do energy concept apply to the descending sandhill grade? Okay, so this is some example. All right, so let's say you see that the eagle. All right, so the eagle is going down. All right, so it's flying and then it's going down. So how energy is going to apply over there. All right, so how to slow down. All right, and then how to move up. All right, and then you see how the thing of energy being stored and transformed from one form to another. All right, so we will see more specific firstly on the gravitational potential energy. So when a particle in the gravitational field of the Earth, there is a gravitational potential energy associated with the particle. So for example, we have the gravitational potential energy we define as U grav equals to mgy. Okay, so it depends on the mass and also the gravitational acceleration, and y is the vertical coordinate of the particle. Okay, so let's say over here we have a basketball. All right, okay, so we have the gravitational potential energy. Okay, is converted to the kinetic energy. Okay, and the basketball speed increases. Okay, so where we have at the, you see that the ball is at the highest point, so it will stop at the moment. All right, you can imagine that. So and then it will go down. All right, so you have at that time, so you have the gravitational potential energy applied. Okay, so we have the kinetic energy after that, which give the speed to the basketball. Okay, so the change of the gravitational potential energy is related to the work done by the gravity. Okay, so for example, we have a box over there. Okay, so we have at y2, okay, and y1. All right, so initial location is y1, and then the box now is at y2. Okay, you see that. So the displacement, what is the displacement? So the displacement is y2 minus y1. Okay, so you see that the displacement is negative. All right. Okay, so the W, okay, so W does the positive work, okay, but you have another force, vertical force, okay, moving upward. All right, so that is cancelling out the W. All right, so over here, okay, because your Y, okay, as you can see that over here, because it depends on Y, so because your Y is negative, all right, so because your Y is negative, so the change, okay, so your U gravity will be less than 0. Okay. Okay, so when the box, all right, when the object moves up, okay, the Y increases, okay, and then the work done by the gravitational force is negative, okay, and then the gravitational, all right, and then the gravitational potential energy increases. Okay, so you can see here that the displacement, okay, now tends to be positive. All right, so because it moves from this point, okay, from this point to that point, okay, and then W does the negative work. All right, and then because why the W does the negative work? Because the box is moved up, okay, so it is reversed to the W, okay, so the W is positive to that direction, but if to that direction it will be negative. So that's negative W. So we have the potential energy increases. Okay, so we have the potential energy increases. So now the gravitational potential energy will be positive. Okay, so hope you're clear with that. Okay, so when the object is going down, okay, then the gravitational potential energy will be negative, and when the object is going up, then the gravitational potential energy will be positive. Okay, so the total mechanical energy of a system. Okay, so we have the concept of the conservation of the mechanical energy. Okay, so the total mechanical energy of system is the sum of its kinetic energy and the potential energy. So it is combination. So you have, because you have movement, all right, you have movement. Um, so when the object is going up, the potential energy will involve, also the kinetic energy involved. And also when the object is going down, it will also involve the potential energy. So potential energy will be negative. Okay, but there is increment of the kinetic energy, right? So when the object is going up, okay, so the kinetic energy of course will decrease, and then the potential energy increases. So that's the concept. Okay, so it's like when you pull the ball, okay, when you pull the ball upwards, okay, at the highest point, of course it will be at the maximum potential energy, okay, and then at almost near to the bottom, so you have the highest kinetic energy, and then the least potential energy. Okay, so that's the concept of of the conservation of the mechanical energy. All right. So example of the conservation of the mechanical energy. So we have, let's say, at the one point we have K1, and we have the potential energy of 1, and then it is equals to let's say an object over here, all right, an object over here, and it moves up over here, okay, so it will have the same, okay, same k plus u, okay, like this one. Let's say here is k1 plus u1, and over here it will be k2 plus u2. It will be similar, okay, to k1 plus u1 and k2 plus u2. Okay, so let's have a look at this video demonstration.
So here I am up on a lecture bench for some reason, holding a bowling ball, which is connected with the wire to the ceiling. I'm going to bring the bowling ball up to my chin, let it go, let it swing away, and come back. Now, why would I do this? I don't know. Is there a possibility I could be injured? Well, the question is, if I let the bowling ball go, swing away, swing back to me, will I be injured?
So do you think that the ball will hit him, right, when the ball swings back? So what's your answer? Yes. You can raise your hand. You can raise your hand. Anyone choose A? No. How about B? You can raise your hand. B. Okay, so majority of you chose B, so it won't be. Okay, let's see.
Let's find out. So as you can see, I'm still okay. Conservation of energy tells us that if you have a pendulum, with the highest point that the pendulum cannot go any higher than that. So when I start it up here, swings away, comes back, can go no higher than its starting point. Now, if I were to start like this and give it a push, then I'd want to step out of the way. I gave it more energy so it could go past its starting point. That you do not want to do. Just want to let it go without giving it any extra energy.
Okay, so that's the concept, right? So if we just release the pendulum, okay, so let's say you're releasing the pendulum, right, and then you are not giving that, you just release it without giving the energy, okay, so the ball will only reach back to the highest point without going to the extra mile, right? But if you give you push it, right, meaning that you give the extra energy, the ball will hit you, right, because there is additional energy, okay, involved with the pendulum. Okay, so that's the concept of the conservation of energy. Okay, so you have, let's say you have K1 plus U1 will be equals to K2 plus U2. Okay, so at any point, okay, so at any point, for example, this one, so this is your pendulum. So it will move like that, all right. Here, you have U1 and you have K1, all right. Here you have U2 and K2, and here you have U3, K3. So it will be similar, all right? U1 plus K1 will be similar to U2 plus K2. It will be similar to U3 plus K3. Okay, so that's the concept of the conservation of energy. All right. So, okay, when only the force of gravity does work on a system, okay, so the total mechanical energy of that system is conserved. So you see a jumper over here. So it's in the athletic jumper. So let's say he moves up, okay. So because it gives already much the forces over there, okay, while jump up, okay. So we have over here the kinetic energy, okay, will decrease, okay, will decrease until at the highest point, and then the kinetic energy will again increase, okay. But the potential gravitational energy will increase, okay, will increase until at the highest point, which is will be at the maximum, and then the potential gravitational energy will decrease, okay. So here the concept of conservation of energy is applied, right? So let's look at example.
In example 7.1, a baseball is thrown straight up in the air at initial velocity of 20 meters per second. We'd like to calculate how high it goes ignoring air resistance. So let's begin with a diagram of the motion. Here the ball is thrown from someone's hand and it reaches its maximum height. We're going to choose our coordinate system such that y equals 0 corresponds to the point where the ball just leaves the thrower's hand, and y2, the height that we're looking for, the position we're looking for, is the position where the ball has 0 velocity at its maximum height. This is a classic conservation mechanical energy problem. The only force acting on the ball as it's traveling up and eventually coming down is gravity, and so we can use the concept of potential energy of gravity as shown in the equation. The mechanical energy at the position y1 must be equal to the mechanical energy at y2, since there are no other forces acting in the problem but gravity. And here's the mechanical energies written out. So to execute a solution, it's very simple. We just need to identify y1 and y2 and v1 and v2. So y1 is equal to 0. Therefore, the potential energy at y1 is equal to 0. The kinetic energy at 2 is equal to 0 because the velocity at position 2 is equal to 0. So our mechanical energy equation greatly simplifies. We simply have the K1 is equal to the potential energy at 2. Putting in the expression for K1, 1/2 mv1 squared, is equal to the expression for the potential energy. We can now solve for y2 as shown. And the answer is 20.4 meters. If we go back and look at the diagram, we note that y1 didn't have to be 0 at this position. We could have chosen it to be anything we wanted. For instance, we could have let y1 be 5 meters. If I come back over here, the only thing that would have changed in this analysis is that this would have needed to be y2 minus 5 meters. And over here, I would have needed y2 minus 5 meters. And again, the difference from here to here would have been the same 20.4. This ends example 7.1.
Okay, so this example is quite easy. All right. So basically, you need to find out what is y2, the height of the ball, okay, at its maximum point. All right. So when you throw out a ball upwards, so basically you have the initial speed, all right, or initial velocity. Okay, so where you have the K1 at the maximum over there, right? K1 is at the maximum, and then you will have the zero potential energy during that time. Okay, because you define that as y1 is 0. All right, and then when this term, right, mgy1 is 0, and then the other term, half mv squared, half mv2 squared is equal to 0. So you have half mv1 squared equals to mgy2. Okay, so you find out what is your y2. So y2, so you cross m, so you have y2 will be equals to half v1 squared. Okay, half v1 squared. So okay, so
the diagram of the motion.
okay, so half v1 squared over g. All right, so you obtain y2 equals to 20.4 meter. Okay, so it doesn't depend, all right, it doesn't depend on the mass, okay, on the mass of the object. Okay, if the initial point is 0. Okay, okay, so right, so we look at this parachute problem. Okay, when the forces other than gravity do work. Okay, so we have the force, okay, acting up, okay, on the parachute balloon. All right, so we have the air resistance. Okay, the force acting up is the air resistance, and the parachutist is going down. So where we have the displacement. Okay, so over here, this is the other forces acted, all right, on the parachutist other than the gravitational force. Okay, so over here we have F other, which is the air resistance, and S are opposite. Okay, so W other, okay, W other is less than 0. Okay, W other is less than 0, and then hence we have the total energy is K plus U gravity. Okay, so that one must decrease. Okay, so let's say the parachutist speed remains constant, so K is constant. Okay, when the parachutist is going down, so the potential energy decreases. Okay, so because over here the kinetic energy remains, okay, because the kinetic energy remains, but we have the potential gravitational energy that decrease. So that's why the parachutist is going down. Okay, all right, so we have an work and energy along a curved path, for example. Okay, so we can use the same expression for the gravitational potential energy where the object path is curved or straight. Okay, so let's say we have an object, okay, is moved up, okay, is moved down, all right. So the box is moved down, going is a little bit curved, all right. So W, the work, okay, at point that Y1, okay, and point Y2 will be different. Then we need to find out what is the W due to the gravitational potential energy. So mgy1, we minus that with mgy2. Okay. So you look over on the B, on the figure B. So the work done by the gravitational force depends only on the vertical component of the displacement y. Okay, so it only depends on the displacement y, because we are talking about the gravitational force. Okay, so that's why we are considering only in the direction of the delta y. Okay, so in that case, we have the delta y as the negative. Okay, because, all right, because the y2 is much smaller than y1. Okay, all right. Okay, so let's look here. So we have, okay, the ball released at different height, okay, and it is going to the different direction, okay. So let's say for number one over here, we have this kind of angle, all right, and then this one making that angle, and we have another one and another one. So we define and this number one, and that's number two, that's number three, and then that's number four. Okay, so over here, okay, at y0, okay, so at y0, so the potential energy, okay, so let's say it is released from the same height, okay, with the same speed but at different angle. So mean that we have kinetic energy is similar. All right, we have kinetic energy is similar at this point, okay, at y0. But at this point, h, okay, we have, okay, this one. All right, so the energy is still similar, okay, but we have certain potential gravitational potential energy due to the height. Okay, you remember that U is equal m g y. So this height corresponds to this h. Okay, so you need to consider that in calculating the total energy involved. Okay, okay, so that's the concept of the conservation of energy. All right, so we have the elastic potential energy. Okay, is elastic if it returns to its original shape after being deformed. Okay, for example, I have this rubber band. Okay, so it has this length. Okay, so if I pull it, okay, and then I release it again, okay, it come back to its original shape. Okay, so we can call that this rubber band has the elastic potential energy. Okay, so elastic potential energy is energy stored in an elastic object. Okay, so we have U, EL. So before that, we have U graph. Okay, U GRAV. So that's for potential gravitational potential energy. And now we have UEL as the elastic potential energy is equals to half kx squared. Okay, so x, if positive, if it is stretched, okay, if it is stretched, okay, x will be more than 0. If it is compressed, okay, if it is compressed, then x will be less than 0. Okay, so it's like our Achilles tendon, all right? So our leg is like a natural spring, okay? When it's stretched and then relaxed, okay? This tendon stores and releases elastic potential energy. So it's like you are trying to jump, all right? If you are trying to jump, okay? So of course you are trying, okay, to put the energy on this Achilles tendon, all right? And then you can go out, okay, and then it will stretch, okay, it will stretch. So but before that, it is like it is compressed, okay. Okay, this the advantage of this is the spring action of our Achilles tendon, right? So reduce the amount of work, okay, your leg muscles must do as you run, okay. So because when we run, okay, so it's like we are not feeling so much force, okay, due to that we have like a spring action, all right, a spring action that help with our work. Okay, we have example here. Okay, this example shows how a spring does work on a block as it is stretched and compressed. Okay, so it is this one at the normal condition for figure A. Okay, it's not stretched or not compressed, and B, it is stretched. Okay, when it is stretched, it does negative work on the block. Okay, so because the force of course the spring we try to pull back the box, okay, and then we have the displacement to the positive direction, x direction, and then when the spring relax, okay, it does positive work on the block, okay, because now it's going to the negative x direction, okay, and then now again after it's compressed, it must go back to its original position. So the spring is forcing to that direction, and s is also to that direction. So this is also positive. Okay, so how do you find that the work is negative or positive? As you remember that W is Fs. So W is Fs. So we have that when F is reversed to S, so of course W will be negative, and then this W will be positive, and this one will be positive. Okay. All right, let's say we have the elastic potential energy graph. Okay, so it is in the parabolic shape. Okay, so example over here, so we have the spring is compressed. So when the spring is compressed, we have the highest elastic potential energy, okay? And when it is released, okay, back to the normal position, you have the zero elastic potential energy, and it will be maximum again when it is stretched. Okay, and you need to note that this UEL, okay, the elastic potential energy is always positive. Okay, is always positive. Okay, you see that this boy is playing on a trampoline. Okay, so this trampoline, okay, have a surface that is elastic. Okay, so this, it will goes back to its original, okay, its original position after it's been stretched. Okay, it's been stretched and then going upward and then going back, okay, down and so on until it retain its normal shape. Okay, so this situation, okay, when this boy is playing on the trampoline, we have the two potential energy involved. One is elastic potential energy and another one is gravitational potential energy. So the sum of the potential energy is summation of both of that. Okay. All right. Why? You see that? You notice that when you jump on the ground compared to you jump on the trampoline. Okay. So over on the trampoline, you will have bigger potential energy. Okay. This is when you jump on the trampoline. Okay. How about if you jump on the ground? You only have U due to U graph. Okay, this is on the trampoline. Trampoline, and this is on the ground. Okay, you notice that you have bigger U, all right, on the trampoline, and you feel that you will have much higher kinetic energy. Okay, you will have much higher kinetic energy when on the trampoline. Of course, you will jump higher on the trampoline. So that's the relationship. Okay, so you have only this energy, okay, and then you will be add with your kinetic energy. Okay, so the kinetic energy will only be equal to maximum as the maximum of this one. Okay, or only on maximum U gravitational U graph, okay, at the maximum point. Okay, but over here your kinetic energy will be combination of these two, okay, which give you, that's why you have much higher kinetic energy when you are on the trampoline. Okay, so you can see that concept. Okay, when you have additional potential energy, of course you will have much higher kinetic energy. Okay, all right, so we look at the conservative and non-conservative forces. A conservative force allows conversion between kinetic and potential energy. Gravity and the spring force are conservative. Right? The work done between 2 points by any conservative force can be expressed in terms of a potential energy function. It is reversible and is independent of the path between the 2 points. Is zero if the starting and ending points are similar. Okay, so this is when the energy is conservative. Okay, so this is applied. Okay, so a force such as a friction that is not conservative is called a non-conservative force or a dissipative force. Okay, so the work done by a conservative force such as gravity depends on only the endpoints of the path. Okay, not the specific path taken between those points. So it only depends on the initial point and also the final position. Okay, so because the gravitational force is conservative, the work it does is same, okay, for all three paths. Okay, so the work based on the gravitational force is similar. So according to any path that you take. Okay, so let's say this runner is taking three different paths. Okay, but actually the work done by this runner due to the gravitational force is similar. Okay, because the final position is similar. Okay, for this runner. Okay, for example, we are checking the tire. Okay, let's say we have an automobile tire flexes as it rolls. Okay, so the non-conservative internal friction forces act within the rubber. Okay, okay, the mechanical energy is lost and converted to the internal energy of the tire. Okay, and then this causes the temperature and pressure of a tire to increase as it rolls. Okay, so that's why it is best to check when to check the tire pressure. Okay, when before the car is driven, when the tire is cold. Okay, so this is the reason why you need to check the tire when the tire is cold, because um, there is no, okay, there is less frictional force acting within the rubber. Okay, okay, so when the tire is cold, there is less friction acting on the tire, because this friction is the actually the force that is non-conservative. So it can be there, and then at the same time it cannot be there. Okay. All right. So we look for another example.
In example 7.11, we're told that in some region of space, an electron feels this force. Notice that the force is always in the y direction, but it is in fact proportional to x. We'd like to calculate the total work done as the electron goes around a closed loop as shown in this diagram. And from this calculation, we'd like to determine whether this particular force is conservative or non-conservative. Now, since the force is not a constant, and it's not always in the direction of displacement, we're going to have to carry out this integral of the scalar product between F and dl, where dl is a differential element along the path. In fact, we can break the path up into the four sides of the square and just add the work done along each side. If the sum of all these is 0, then we'll assume that then we will conclude that the force is conservative. If it's not 0, then it's a non-conservative force. So we begin with leg 1 and going from this position to this position. And the first thing that we notice is that the force is always at a right angle to the motion. And so trivially, the scalar product is 0 and the work along leg 1 is 0. For leg 2, however, the force is straight up and it's a constant along this leg because we're always at x equal L. And so the work is simply going to be the force times the distance. I can pull the force out of the integral, and I just have the integral of dy from 0 to L, which is going to be L, and the work is c times L squared. For leg 3, again, the force is at a right angle to the motion, the path, and so the work is going to be 0 along that path. And for leg 4, in principle, I could have a finite work, but in fact, the force is 0 here because x is equal to 0 on this leg. So again, I find that the work is equal to 0. The total work in going around the square loop is in fact CL squared. The starting and ending points, I start at the origin and go around and end up at the origin, are the same, yet I pick up a finite amount of work, and so this is definitely a non-conservative force. This force cannot be represented by a potential energy function. We note that in fact, as the electron goes around, it picks up energy, CL squared, and if in fact I had gone around the opposite way, I would have had 0 on 3 of these legs for the work done, but on this leg, the work would have been negative, and this would have been minus CL squared for clockwise rotation. And this ends example 7.11.
Okay, so in this problem is
example 7.11. We'd like
asking about the force, okay, when the electrons is moving on a square, right? So it is given that the force, right, is CL, okay, the force is CL, and J is just the direction of that, okay. So we need to integrate all of these forces, all right? So F dot dl, okay? So if you know that, so dl is in terms of the direction, okay? If F is perpendicular to dl, so for the dot product, it will be 0. Okay? So when it is perpendicular, it will be 0. So there will no work done, okay, to that direction. Okay, so
path. The product is 0, and the
okay, for the first one, okay, so for leg 1, so it's going from 0, 0 to L0, okay. So the work is 0 because this force is perpendicular to the DL, okay. And then for leg 2, it is parallel. So when it is parallel, there will be work, okay. So what's the work? So you need to do the integration. So LL to L0. So it will be L minus 0. So you replace that. So the force will be CL. Okay. So the force will be CL. So CL. And you replace that. Okay. So dy, when you do the integration dy, so C will be y. Okay. So CL y. Okay. So CL. So when you expand this integration, it will be CL L. So that's why you have CL squared. Okay. So CL L minus 0. Okay. So you have CL squared. Okay, and also leg 3, because it is perpendicular, then you will have the work as 0. And then it's going down. So when it's going down, F now is 0. So you can see that now F is 0. So you only have F when it is at x of L0, okay? When x is at L0, but not when x is at 0, okay? So you have for 0. So when you're for 0, even though it is parallel, so if because even though is DL is parallel to F, your work will still be 0. So we notice that when the work is not 0, it is a non-conservative force. So it is not a non-conservative force. When electron moves around a square loop, okay, in the XY plane. Okay, so hope you can distinguish that. Okay, so the non-conservative force do not store potential energy, okay? But they do change the internal energy of a system. The law of conservation of energy means that energy is never created or destroyed. It only changes form, okay? So this law can be expressed as, okay, delta K plus delta U plus delta U internal, okay, and it will be 0, okay. So this is like a concept of, okay, whatever you involve, okay, let's say you have just the problem of trampoline, so you have the gravitational U, okay, and then this U internal from the elastic potential energy, okay, so you must add it, okay, to obtain that. So that will be equals to K, right? So this is for conserving the, for to obtain the concept of conservation of energy. Okay, so let's look in one dimension problem. So in 1D, a conservative force can be obtained from its potential energy using Fx equals to minus du over dx. Okay, the differentiation of u over x. Okay, in the regions where ux changes most rapidly with x, this corresponds to a large force magnitude. Okay, also when fx x is in the positive x direction, okay, ux decreases with increasing x. Okay, a conservative force always acts to push the system towards lower potential energy. Okay, so we look over here. So we have elastic potential energy force as function of x for an ideal spring. For example, here. Okay, so we have the elastic potential energy as and force as a function of x. So elastic potential energy, okay. So we have that, okay. We notice that the potential energy cannot be negative. So we have a parabolic shape. Okay, so so the equation of this, okay, is U equals to half kx squared, and then the potential energy is minimum. Okay, it's minimum at x0. So over here, the kinetic energy is at maximum. Okay, and then so we look at the force. Okay, we look at the force. So the force, when we differentiate this, okay, so we obtain this. Okay. Okay, so for x, less than 0, Fx is bigger than 0. Okay, so the force pushes body towards x0. So it force push towards x0. So that's why, okay, so it's like a pendulum problem. So when it's over here, so you try to push back, okay, so you have force, okay, acting towards that. Okay, so when it is on the other side, okay, it will be reversed. Okay, so Fx will be in the negative. Okay, so try to push back the body towards x equals to 0. Okay, so that's why we have the negative force over here and then positive force over here. Okay, and it will be 0 at the center of that. Okay, so that's the force Fx. Okay, relates with the potential energy. Okay, so for the example of gravitational energy, so how it is defined. So the potential energy of the gravitational potential energy, it can be negative, right? So when it is 0, it is 0 when the kinetic energy is maximum. Okay, and here at the highest point. So at the highest point, okay, and this, okay, it is when, okay, it is at the point that is lower than this higher point. Okay, so over here you can see that the potential energy decreases as y decreases. Okay, and then the potential energy increases as y increases. Okay, so over here Fy is constant. Okay, so for all y, Fy will be 0. Okay, because the force pushes body towards decreasing y. So it will be minus mg. Okay, so that's the difference between elastic energy and also gravitational energy in terms of its forces. Okay, how about in 3D? So in the 3 dimensions, the component of conservative forces can be obtained from its potential energy function using the partial derivative. So we have a component of x, y, and z. So we need to derive for all of that 3 components. Okay, when we take the partial derivative of u with respect to each coordinate, so we need to multiply the corresponding unit, the vector, and then take the vector sum. Okay, this is called the gradient of u. So gradient of u is the summation of all of the partial derivative of this one. Okay, so let's look for example.
In example 7.14, a puck with coordinates x and y is acted on by a conservative force described by this potential energy function, where k is a constant. We'd like to find the corresponding force. But if you have the potential energy function, you can always find the force by taking the negative of its gradient. In particular, the x component is minus the partial u respect to x, and so forth for the y and the z components. Because this function doesn't depend upon z, the z component of the force will be 0, and the magnitude of the force is obtained in the usual fashion. So now we can calculate the two components of the force. The x component is minus kx, and the y component is minus ky. In unit vector notation, the force is minus k times this. The magnitude of the force is just k times the square root of x squared plus y squared, and I recognize that as the distance from the point xy to the origin. So I can write that as k times r. I can actually rewrite the force in this form, where r is simply a vector, position vector corresponding to the point xy. And I note that u can be written as 1/2 k r squared, where r squared is x squared plus y squared. And I can now differentiate u respect to r with a minus sign, of course, and I get minus kr, which is what I have here. So as we found above, the force has a magnitude of kr, and actually the force points towards the origin because of this minus sign. And this ends example 7.14.
Okay, so this is example of the air hockey table. All right, so
Acted on by conservative.
So you know that the game, all right, the air hockey, where we
like
push
to
it,
find the
so
corresponding force.
it is a frictionless,
If you
all
have
right,
a
it is a
potential energy
frictionless
function, you can
hockey
always
table. So we have that, so it move in x and y direction. Okay, so it move in x and y direction. So it's given that u will be function of x squared and y squared. So because originally, if you see in one dimension, it will be half kx. Okay, and now we add the term of y, so it will be half k in the bracket x squared plus y squared. Okay, so we need to find a force, okay, acting on the puck. Okay, so how do we define it? So we use the gradient of that. So the gradient of that, so we have force. Okay, so it is a partial derivative of all of the components. So we have du over dx plus du over dy and plus du over dz.
Z components.
Okay. So
now we can calculate the two.
du over dz will be 0, of course 0, and then f, okay, will be in terms of, okay, in terms of squared, okay, square root of fx squared plus fy squared. So because this is the force that is acting on that, is only dependent on the x and y. Okay, so we look here. So what do we have here? So if we derive this, okay, if we derive this, so du over dx, so it will be minus kx. Okay, and for fy, we have minus ky. All right, so f will be equal to minus kxi plus minus kyj. Okay, so when you combine this, it will be minus k in the bracket xi plus yj. Okay, then how do you convert this? X, y. So in terms of the magnitude of this, right? In terms of the magnitude of this, so you will have that, okay, f will be equals to square root of, so that's minus k, x is fx, right? So you replace here, okay, squared plus minus ky squared. Okay, so then finally you obtain as k square root of x squared plus y squared. Okay, which you define that the square root of x squared plus y squared is r. Okay, you know that x squared plus y squared is like a Euclidean distance, right? So it is a distance from one point to another point.
Times r.
Okay, so when you plot it on the graph, So
It's simply a vector.
that's your R. Okay, so that's your R. So you can see that
Position vector
to that
corresponding
direction.
to the point x, y. Squared, where r squared is x squared plus y squared. And I can now differentiate u respect to r with a minus sign.
Okay, so that's the force. Alright, so that's the force, which is F is equals to K square root x squared plus y squared. Okay. Alright. So that's how to solve that question. Alright, so let's say we have example of the greater the elevation of a hiker in Canada's Bank National Park, the greater the gravitational potential energy. Okay, so when we hiker, so when it hikes the hill, of course, it will has the highest potential energy at the peak, right? So when the mountains has steep slopes, so U graph has a large gradient and there's a strong force pushing you along the mountain surface towards the region to the lower elevation. Okay, so there's a zero force along the surface of the lake, okay, which is at the same elevation. Okay, so when the top and it's going down like that, so it will be, you will have the strong force, right? So when pushing that, so it will be strong force because you see that the gradient or the slope will be high. But when you are on the elevated surface or the horizontal surface, then it will be zero force, okay? Because your U gravitational will be similar, okay? It will be similar at every point on the lake. Okay, so we look at the energy diagram. So an energy diagram is a graph that shows both the potential energy function Ux and the total mechanical energy E. Alright, so the figure illustrates the energy diagram for a glider attached spring on the air track. Okay, so we have a glider there. Okay, for example, so it's attached to a spring on the air track. Okay, so we have at the position of O, okay, which is the original position, and then to the left, okay, minus A, so where the spring is compressed, and A, where the spring is stretched. Okay, so of course, you have that this graph of the kinetic potential, elastic potential energy. Okay, so you look there, so you have that equation of E equals to K plus U, and U is defined by half Kx squared. Okay, and then force and graph on of its potential energy function. Okay, for any graph of potential energy versus x, the corresponding force is Fx equals to minus du over dx. Okay, whenever the slope of u is zero, the force there is zero, and this is a point of equilibrium. Okay, when u is at a minimum, okay, the force near minimum draws the object closer to the minimum. So it is restoring force. This is called a stable equilibrium. Okay. So when u is at the minimum, okay, the force near the minimum draws the object closer to the minimum. So it is a restoring force. Okay. when U is at maximum, the force near the maximum draws the object away from the maximum. This is called the unstable equilibrium. Okay, so you look at this, for example, this is acrobats, okay? It is at the, okay, at having a certain potential, gravitational potential energy. So it is in unstable equilibrium, okay? So the gravitational potential energy is lower no matter which way an acrobat tips. So if she begins to fall, okay, she will keep on falling. Okay, so meaning that to ensure that the acrobats, okay, stay in balance, so the acrobats needs constant attention. Okay, so to balance on this high bike, okay, so she needs to ensure that the point, okay, so that's why need to use the hand. Okay, so it actually helps, okay, it helps with the balancing the equilibrium point, okay, of the body. Okay, so that's why the, okay, so that's why the acrobats can still keep, okay, that can still keep their body, all right, on the top of the bike. Okay, when she's alone, okay, when she's alone, it will be much more, okay, it will be much more unstable, okay, because, okay, because that the force, all right, acting on that, okay, is much lower, all right, is much lower, and then causing that she feel like to fall, rather than if they are holding hands together. If you see in the picture, it will be much more stable. Okay, so it is more challenging for the acrobat when she's alone actually, rather than when they are in the team. Okay, so one more point, it said that the, okay, when the acrobat fall, okay, it will keep falling, okay, because you will have the gradient of the force is high. Okay, gradient of the force is high because it moves with the acceleration now, okay, when it falls. So that's why when you fall, okay, it is hard for you, okay, to keep your balance back, okay, when you are at the actually highest kinetic energy, okay, unless you are at the point, okay, where your kinetic energy is still small, all right, because you have the potential energy at the time is still bigger than the kinetic energy. All right, so that's it for today. All right, so I already finished with the chapter 7. So on Thursday will be your test 1. Okay, so that will covers until chapter 5. Any questions so far? No questions. So tomorrow will be our tutorial session. Okay, so you must submit the tutorial by today. Okay, so for the one that we discussed on the last 2 weeks, all right, so which is chapter from chapter 2 and chapter 3. Okay, so tomorrow will be more extensive tutorial, so because that one will involve chapter 4, 5, 6 and 7. All right. Okay, so if there is no question, so let's turn on the camera and we take attendance together. Okay. So Munira is always enjoying the morning outside. All right. Okay, so let's count from 10. So 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Smile. Okay, one more shot. All right, so I see you tomorrow during the tutorial. So if you have any question, let me know. Probably I'm going to give you some more tips for the test 1 tomorrow as well. Okay, so see you tomorrow. So all the best for your test 1. Okay. So that's it for now. Assalamualaikum and bye-bye. Okay. See you.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor. Thank you, Doctor.
Welcome.
Thank you, Doctor.